Okay. So yeah, he gave hydrogen a mass of 1, weighed some other things. Carbon's 12 times heavier. Its mass is 12. Oxygen's 16 times heavier than hydrogen. Its mass is 16. And we see that roughly reflected in the periodic table that we have in front of us. But again, we do see now those decimals because we know that there's different versions or isotopes. All right. So the cool thing that we can do here is actually figure out our like how different things react with each other, and find out the mass of different compounds. So, for example, the reaction between 2.74 grams of hydrogen gas and 97.26 grams of chlorine gas makes 100 grams of hydrogen chloride. So, assuming hydrogen chloride contains 1 hydrogen and 1 chlorine, so that means that it's HCl. And they're calling it hydrogen chloride, so this is in a gas form, not as an aqueous acid. We're asking, what is the chlorine atom's relative mass? Okay, so if we go like this, 97.26 grams of Cl, and we divide that by 2.74 grams of hydrogen, what we end up with is, I think, 35.56. So that means that there's 35.56 grams of chlorine for every 1 hydrogen. So this means, therefore, Cl is 35.56 times heavier than hydrogen, and has a relative mass of 35.56. Is this grams? Yeah. If we're dividing gram by a gram, they're going to cancel out, right? So this has got actually a different unit. It's not in grams. We're going to end up calling it atomic mass units, but we'll get to that. Just know that when you're doing that division, we're ending up with a number that is not as grams. Okay, so originally we used hydrogen to compare. So it was the standard to compare. All other elements because it was the lightest element. So it's pretty easy to go like some ratio to 1, right? But then it was changed to oxygen. And then finally, we ended up changing to carbon-12, which is what we use now as our standard. And it was assigned a value of 12.0000. So carbon-12, so carbon that has got 6 protons and 6 neutrons, carbon-12 is our standard for comparing all other elements at this point. And we use it quite a bit. It was actually interesting. So my dad is pretty old. He's like 73, I think. He's 73. And he went to school for chemistry. He went to university for chemistry. And I was like, Dad, I'm teaching chemistry. I'm so excited. And then we were talking about some stuff that we're going to get into in this unit. And he was like, what are you talking about? This thing's based on oxygen's atomic mass. And I was like, no, Dad, it's based on carbon's atomic mass. So he pulls out his like old high school textbook, his like chemistry 12 high school textbook, which is from like the 1960s. And he's like, look, oxygen. And I was like, no, Dad, Google carbon. But it was kind of funny to see that this just happened over the last like I don't know, the last like 60 something years, we've gone from oxygen to carbon 12. So changes, they're made all the time. Okay, so the masses of individual elements, or individual atoms rather, are assigned a unit of relative measure. So a unit of relative measurement in relation to carbon 12. And this is called our atomic mass unit, or AMU. It is defined as 1/12 of the mass of carbon 12. That is hard to read, but it says 1/12. So 1/12 the mass of a carbon 12 atom. And then because hydrogen has 1/12 the mass of a carbon atom, they have a relative mass of 1 AMU. I'm going to just fact check myself on something before I say it out loud. Okay, yes. Good, I was right. All right, so the reason that we don't use hydrogen, so it seems like, hey, why don't we just keep on using hydrogen if it has a relative mass of 1 AMU? Hydrogen can exist much more frequently as having 1 or 0 neutrons. So it actually will fluctuate in its atomic mass more than carbon 12. So carbon 12 is just like really consistent, very common. So this is our preferred one that we like to use. Because it seems weird that we wouldn't just use hydrogen if it's a 1, but it just is, it's less consistent, I guess, in our environment. Oh, whoops. I did not print off the next sheet of this. All right, so if we're looking back at our last example, our chlorine atoms are 35.56 times heavier than hydrogen atoms. They have got an atomic mass of 35.56. And we are going to watch a little video about measuring atomic mass. And Dalton's theory. Does everybody remember conservation of mass from last year and balancing chemicals, balancing equations? How confident do you all feel with balancing equations from like, yeah, I love balancing equations down to like, what? I don't remember how to do that. Or, yeah. Okay, sweet. So we will do some practice with that. But this is just explaining that conservation of mass thing. So we've got, we can't create or destroy. We have to have balanced numbers on each side. Okay. So Dalton's relative mass scale, it was a little bit incorrect because as we just saw, a lot of elements are actually, or a lot of compounds rather, are actually not just those simple compounds that he was seeing, but are made up of multiple elements. So it was partly incorrect because not all of the molecules he studied actually only contained one atom. of each element. So for example, maybe he was looking at CO2, but using, like, doing math and calculating things, but like using it as CO. So just thinking that it was made up of one of each rather than three things. So then his math would have been off and he would have been finding incorrect numbers for those relative masses. Okay, so then, and that was a long time ago, right? So science has evolved quite a bit since then. So he found a really amazing hypothesis, a really great theory, and then it's been built on over time. And this is one of the things that we found that was not quite right, that needed to be changed. So then this guy, Joseph Gay-Lussac, which I'm probably really butchering. I don't speak French. He was a French chemist. So he was from 1778 to 1850. And when was our guy John again? John was 1766 to 1844. So there was a little bit of, there's a lot of overlap there. He studied how gases reacted. And then he looked at how pairs of gases reacted at the same temperature and pressure. And that's really important. Does anybody have a thought on why, like, the same temperature and pressure might be important for gases? What happens when you have got, say we had one gas, and this was low pressure, and then we had another gas at high pressure. Would there be a consistent amount or volume of particles in each of those? No. Which one would likely end up having more actual atoms in it? High pressure, yeah. So high pressure, we're squishing things closer together. Low pressure, we've got things further apart. So it's very important that he was studying these the same temperature and pressure. What about temperature? Why would that be important? Yeah, totally. So the things that are at a higher pressure, or sorry, higher temperature, are going to move around faster, and lower temperature, they're going to be moving around slower. So these two things being constant was very important for what he learned. Okay, what he determined: 1 liter of hydrogen gas reacts with 1 liter of chlorine gas to make 2 liters of HCl in a gas form. 1 liter of nitrogen as a gas reacts with 3 liters of hydrogen as a gas to make 2 liters of NH3 gas. And 2 liters of carbon monoxide gas reacts with 1 liter of oxygen gas to make 2 liters of CO2 gas. All right, are these numbers consistent with the number of particles, the number of atoms in our actual end results? So if he's combining 1 liter of nitrogen, we've got 1 nitrogen for every 3 liters of hydrogen gas, and we've got 3 hydrogen. So he is actually figuring out the chemical composition of these with measurements as liters, which is pretty cool. So by itself, this data did not really seem to be related to the puzzle of how to determine atomic masses. But then what happened is an Italian chemist proposed this really cool hypothesis, which is like a key piece of chemistry that we're going to come back to again and again. Equal volumes of different gases at the same temperature and pressure. Contain the same number of particles. So then if we go back up here, okay, 1 liter of hydrogen gas contains the same number of particles as 1 liter of chlorine gas, if this hypothesis holds true. So then we can say, okay, there's 1 hydrogen for every 1 chlorine in our end result. So now, once this hypothesis is made, we can then kind of go back and actually start using this to determine atomic masses. So therefore, if 1 liter of one gas, we'll call it gas A, reacts with 1 liter of another gas that we'll call gas B, there's exactly the same number of particles as A and B. There's exactly the So the molecule formed is then going to have 1 A for every 1 B. So the formula for that compound would just be AB. And then if 2 liters of gas A reacts with 1 liter of gas B, that's going to mean we're going to have twice as many of atom A as B. Be 2 times So 2 atoms of A are combining with 1 atom of B, and it's going to form a compound A, B, and then we're going to have to use the subscript here, 2, to indicate that there's 2 A's for every 1 B. So A2B. And if we look back at the example up a little higher, what we're seeing is 2 liters of HCl. So that was the 1-to-1 ratio, just like down here. And then we're seeing like the 1-to-3 ratio here. So we are actually seeing that makes sense. I'm just about done. Are you okay to wait like 1 minute? Okay. All right. So this is what leads us to this concept that we will talk about tomorrow called the mole and Avogadro's number, which is going to be like super, super, super important. And we're going to have it memorized. And we might have a day where we like celebrate this number because it's really cool. Kind of like Pi Day, but we'll call it Mole Day. So what we're going to start with tomorrow is relative mass and the mole, a guided inquiry. And we're not going to do textbook questions for this one. We're just going to do this guided inquiry thing. If you would like to start on it today, you're welcome to. But we are going to watch a video about International Women's Day. So this is what that looks like. There are copies of this up at the front. Also, before you leave today, please do make sure that you hand in your Unit 4 self-evaluation, your element, and get a Chapter 5 self-assessment. So just take a second to pack up your stuff, and then I'm going to put on this this International Women's Day presentation. How do I stop recording this? Hey. Okay. All right. Grab one of the self-evaluation sheets. Oh, and did you need one of the Unit 3 ones? I just put them right by the hand in bin there.